Hello, and welcome. Today, we'll be exploring a fascinating and complex topic at the intersection of chemistry, medicine, and society. We're going to take a deep dive into a review article from ACS Chemical Neuroscience titled The Dark Side of Total Synthesis: Strategies and Tactics in Psychoactive Drug Production. This paper, by Schuyler Chambers, Jenna D'Souza, Eric Huseman, and Stephen Townsend, provides a unique look at the chemistry behind some of the world's most well-known and often abused substances.
For millennia, humankind has used and abused psychoactive drugs. Formerly, a psychoactive drug is any substance that alters our cognition and mood. This term is neutral. It covers everything from prescribed medications for pain and anxiety to illicit substances of interest to governmental drug policy. These drugs are a double-edged sword. While they are crucial for managing medical conditions, they are also used recreationally, which can lead to profound societal problems. The authors frame their review against the backdrop of the current opioid epidemic, which they call the deadliest drug crisis in American history. They note that overdose, largely fueled by opioids, is the leading cause of death for Americans under 50, claiming around 64,000 lives in 2016 alone. From a chemist's perspective, this raises a critical question. In what ways, if any, did organic chemists contribute to this problem? This review aims to answer that by providing historical accounts of the main classes of psychoactive drugs and discussing the foundational total syntheses that provided the groundwork for producing these molecules, not just in academic and industrial labs, but in clandestine settings as well.
Let's begin by understanding how these drugs work. Psychoactive drugs affect our cognition by influencing the operation of neurotransmitters in the central nervous system. They do this through one of three general mechanisms. First, as agonists, which mimic the action of a neurotransmitter. Second, as antagonists, which block the action of a neurotransmitter. Or third, by blocking the reuptake of neurotransmitters at the synapse, effectively increasing their concentration. In this way, these drugs often mimic or enhance naturally occurring states of consciousness. Sleeping pills promote drowsiness, for example, while benzodiazepines create a state of relaxation. However, long-term use often leads to tolerance, where a user needs to increase the dosage to get the same effect. As use increases, dependence can develop in one of two forms. The first is psychological dependence, where a user feels an urge to use the drug but faces no physical risk from stopping. The second, more serious form is physical dependence, where withdrawal causes severe physical and mental effects. While the goal of this review is to explore the synthetic strategies behind these molecules, the authors make it clear that we cannot ignore the dark and highly politicized nature of the topic. The scholarly exercises carried out by organic chemists have undeniably guided illicit drug production. The paper notes that virtually all known civilizations have used psychoactive drugs, whether to self-medicate, to anesthetize from trauma, or for recreational and religious purposes.
In the United States today, aggressive marketing of painkillers has led to a generation of individuals with opioid use disorders. The current crisis is not the first of its kind. During World War II and the Vietnam War, amphetamines were used to empower soldiers, while sedatives were used to prevent mental breakdowns. The crack cocaine epidemic of the 1980s and 90s devastated low-income urban communities, while backyard-produced methamphetamine hit poorer rural areas in the following decades. A key difference with the current opioid epidemic is that its genesis was at the pharmacy counter, and it cuts across all demographic groups. From a chemistry standpoint, the current crisis can be traced back to the introduction of OxyContin. Oxy is a semi-synthetic opioid structurally similar to morphine. Historically, strong analgesics like this were reserved for severe pain from cancer or surgery. But in the mid-1990s, oxycodone was marketed for chronic pain. As opioid use increased, distribution spread from doctors to dealers, often through poorly regulated pill mills. The problem grew so rapidly that by 2009, the American Public Health Association published a report titled The Promotion and Marketing of OxyContin: Commercial Triumph, Public Health Tragedy. Ultimately, the closing of these pill mills, combined with an inability to treat the resulting addiction, began a new, darker chapter: the resurgence of heroin and the emergence of fentanyl. This has led to nearly 1,000 deaths per week from drug overdose in the United States. The problem is so vast that the illicit drug trade is now the second most lucrative industry in the world, surpassed only by weapons. The authors point out a striking paradox. The two drugs that cause the most damage worldwide, tobacco and alcohol, are legal in most countries. And the world's most popular stimulant, caffeine, is legal and unregulated. This highlights the complex question of what role organic chemistry plays in this field. As we'll see, legendary figures in chemistry have used these molecules as training tools for generations of students. And while these academic pursuits are scholarly, they create a dichotomy. The lessons learned in the university lab can assist in fueling both licit and clandestine drug use.
Historically, academic syntheses have focused on novel strategies and tactics, while industrial efforts have focused on scale and efficiency. Clandestine synthesis, meanwhile, relies on operational simplicity and the availability of starting materials. The de novo total syntheses from academia are often translated into large-scale semi-syntheses in industry, which are then further simplified for illicit manufacturing. With that context in mind, let's begin our exploration of the chemistry, starting with the class of molecules at the heart of the current crisis, the opiates. Opium extracts have been used for millennia, with the earliest references to the cultivation of the opium poppy, Papaver somniferum, predating 4000 BC in Mesopotamia. Known as hul gil, or the joy plant, its cultivation spread along the Silk Road, eventually becoming the catalyst for the opium wars in the mid-1800s. Let's clarify some terminology. The authors use the term opiate for any compound, natural or semi-synthetic, that shares a structural homology with opium alkaloids. They use the term opioid for substances that produce similar effects on the central nervous system, but do not share that structural homology. Opiates and opioids act on the central nervous system to produce effects ranging from pain relief or analgesia to sedation. Structurally, the opiates mimic the body's natural pain relievers, the endorphins. They feature a complex pentacyclic or 5-ring scaffold. While the structures can look very different, most active opiates and opioids follow what is known as the morphine rule. This rule identifies 4 key structural features generally required for activity. First, a tertiary nitrogen with a small alkyl substituent. Second, a quaternary carbon, which is a carbon atom bonded to 4 other carbon atoms. Third, a phenyl ring attached to that quaternary carbon. And fourth, a 2-carbon or ethyl linker between the quaternary carbon and the tertiary nitrogen. This complex architecture has inspired synthetic chemists for decades, from the first synthesis of morphine in 1952 to the present day.
The opium poppy itself contains several natural opiates. By weight, it's about 8 to 19% morphine, 1 to 5% codeine, and 1 to 5% thebaine. Morphine is a powerful analgesic, the standard against which new pain relievers are measured. Codeine is a less potent analgesic and is also used as a cough suppressant. Thebaine and another opiate, Oripaven, are not used directly as drugs, but serve as starting materials for semi-synthetic opiates.
Let's begin with morphine. First isolated in the early 1800s, morphine's structure was proposed by Robinson and later confirmed by the total synthesis from Marshall Gates and X-ray crystallography by Hodgkin. Despite many synthetic efforts, there is still no practical source of morphine, either by chemical synthesis or fermentation, that can compete with simple isolation from the poppy. The first total synthesis of morphine, completed by Gates in 1952, is a landmark in organic chemistry. It begins with a dianophile, molecule 14, which undergoes a Diels-Alder cycloaddition with butadiene to form the racemic adduct 15. A reductive hydrogenation and cyclization then closes what will become the piperidine D ring. After 6 more steps, including a chiral resolution to separate the enantiomers, they obtained the tetracycle -18. 2 major challenges remained: inverting the stereocenter at carbon 14 and closing the final dihydrofuran-like E-ring. They achieved this through a series of steps involving bromination and hydrazone formation, which allowed for epimerization to the more stable product. Hydrolysis and hydrogenation gave intermediate -19. They then used a similar bromination and hydrazone strategy to simultaneously close the E-ring and install a double bond. Finally, reduction of an enone and cleavage of an aryl bromide gave -codeine, which was then converted to -morphine.
More recently, in 2014,
the Gaunt lab reported a formal synthesis of morphine. A formal synthesis is one that produces a known intermediate that has previously been converted to the final target molecule. Their route began with isovanillin and used a Noyori transfer hydrogenation to produce a chiral aldehyde. A key step was a metal-mediated intramolecular oxidative coupling, followed by a Michael addition. The resulting enone was carried through several more steps, including a Lusch reduction and a dehydrative ring closure, to ultimately produce intermediate -al28, which completed the formal synthesis. Third noteworthy synthesis was reported by the Fukuyama lab in 2017. This route employed a retroaldol-aldol sequence to build a key tetracycle, which was then converted to a diene. A Diels-Alder cycloaddition with singlet oxygen, followed by fragmentation, yielded an enone. Several more steps, including a 1,6 conjugate addition, gave codenone, which was then reduced to -codeine and finally converted to -morphine. This brings us to codeine. Codeine is used for moderate pain and cough suppression. It's less potent than morphine and is usually taken orally. Because of its availability, it's also commonly abused. When cough syrup containing codeine is mixed with soft drinks, it's known as lean or scissor, a practice that has been associated with a number of deaths. Synthetically, codeine is a key intermediate in most morphine syntheses. In 2002, Barry Trost's lab published a synthesis of -codeine. Starting with a chiral cyanoaldehyde, they used a Corey-Fuchs olefination and dehalogenation to form an alkene. A key intramolecular Heck reaction was then used to close the B ring. After oxidation and reduction steps, they formed an amine, molecule -39. The final ring closure was achieved via an intramolecular hydroamination, which interestingly required irradiation with light to proceed. The lab of Gilbert Stork published a synthesis of racemic codeine using a different strategy. Their key step was a Diels-Alder cycloaddition that established both the B and C rings in a single move. They heated aldehyde 41 and its partner in a sealed tube to produce the Diels-Alder adduct. After 10 more steps, the resulting amine underwent a ring closure to form the E ring. Protection of the amine, followed by oxidation and reduction, yielded racemic codeine.
Now let's turn to the illicit semi-synthetic opiates. While morphine and codeine are important, many therapeutics are made by chemically modifying these natural products.
First is hydromorphone, also known as Dilaudid. It's a potent semi-synthetic opiate that is structurally identical to morphine, except for an additional oxygen at the C6 position, which makes it more water-soluble and more effective. Recently, the Hudlicki group published a chemoenzymatic formal synthesis of the enantiomer of hydromorphone. They began with a simple benzene derivative and used an enzymatic dihydroxylation to create a chiral diene. In a key sequence, an oxidative phenol dearomatization was followed by an intramolecular Diels-Alder cycloaddition to establish the B and E rings in a single step. This led to intermediate +50. After rearomatization and tosylation, they reached bis-tosylate -51, intercepting their previous synthesis and completing the formal synthesis. Next is hydrocodone, a component of the well-known analgesic Vicodin. Synthetically, it also serves as an intermediate for codeine and morphine. The most industrially scalable synthesis was developed by Kenner Rice. It begins with the condensation of a carboxylic acid and an amine. The resulting amide undergoes a Friedel-Crafts-like acylation to build the core ring system. A selective Birch reduction is followed by several steps to set up the final cyclization. A key feature is a bromine atom at the C1 position, which is critical to ensure the desired ortho ring closure. After cyclization, an alpha bromination followed by a 5-exotet ring closure establishes the E ring. Finally, reductive annonation and removal of the aryl bromide gives racemic hydrocodone. In contrast, Mulzer and Trauner published a synthesis of negative hydrocodone. Their route began with an aldol condensation and a Robinson annulation. The resulting racemic anone was resolved using chiral chromatography. A 1,4 addition of a Grignard reagent, followed by trapping with a silyl group, set the stage for bromination. Heating this intermediate led to the closure of the E ring. A hydroboration oxidation installed a primary alcohol, which was then elaborated through several more steps to a protected amine. A final dissolving metal reduction liberated the amine and triggered a reductive closure of the D ring, ultimately yielding negative hydrocodone.
Oxycodone is structurally identical to hydrocodone,
but with an additional oxygen atom at the C14 position. Industrially, it is made via semisynthesis from thebane through a redox sequence. The first total synthesis, which avoids thebane, was reported by the Fukuyama lab. Starting from an aryl bromide, they used a Fagnu palladium-catalyzed direct acylation to close the B ring. A key step was an oxidative dearomatization that installed the C14 hydroxyl group.
An intramolecular Michael addition then formed the benzylic quaternary carbon.
In the endgame, an amide was treated with an iodine-3 oxidant to induce an oxidative Hofmann rearrangement. The resulting amine opened a neighboring lactone to reveal the C14 alcohol and establish the piperidine D ring, which was then converted to -oxycodone. Two other important semisynthetic opiates are buprenorphine, brand name Subutex, and naloxone, brand name Narcan. They are used to treat drug dependence and overdose respectively. Buprenorphine is a partial mu receptor agonist, with less abuse potential than methadone. It's often sold in combination with naloxone under the brand name Suboxone to deter abuse. Naloxone is a mu receptor antagonist that is FDA approved for the emergency treatment of opioid overdose. Synthetically, buprenorphine is made from oripavine. An endoselective Diels-Alder cycloaddition with methylvinyl ketone, followed by a Grignard addition and hydrogenation, provides buprenorphine. The diastereoselectivity of the Grignard addition is rationalized by a model where the oxygens of the carbonyl and a nearby methyl ether coordinate to the magnesium of the Grignard reagent, locking the carbonyl in place for a topside attack. Similarly, the Hudlicki group recently reported a semisynthesis of naloxone from oxymorphone. After acetate protection and amine oxidation, dehydration with the Burgess reagent gave an imine. This species is proposed to undergo a 5-endo-trig ring closure to form an oxazolidine. The oxazolidine is then protected as a dimethylacetal to allow for a clean opening with a vinyl Grignard reagent. Hydrolysis of the acetal then reveals naloxone. While most opiate abuse is enabled by prescriptions, some opiates are illicitly synthesized. Heroin was first synthesized from morphine in 1874 and introduced for medical use in 1898. Its addictive potential was not recognized for years, and it was made illegal in the United States in 1924. The paper describes the illicit synthesis of heroin as documented by the Counter-Narcotics Police of Afghanistan. The process starts with raw opium. Treatment with lime, calcium oxide, and hot water creates a two-phase mixture, with the morphine base in the lower aqueous layer. This layer is siphoned off, and treatment with ammonium chloride precipitates the morphine base. This solid is then treated with about 5 equivalents of acetic anhydride to convert the morphine to heroin. After neutralization, the brown heroin base precipitates. It's then purified with activated carbon and finally treated with hydrochloric acid and acetone to give the salt, heroin hydrochloride. Another illicit opioid is desomorphine, or crocodile, named from the Russian word for crocodile. It became popular in Russia around 2003 and is synthesized from codeine. It has been sensationalized as a drug that turns the user into a zombie, as it can cause severe skin discoloration, infection, and necrosis. The synthesis begins with extracting codeine from tablets using pipe cleaner, gasoline, and hydrochloric acid. The resulting codeine hydrochloride salt is then reduced using iodine and red phosphorus in what is known as a Nagai-type reaction. This concludes our look at the opiates. Next, we'll examine the opioids. As we mentioned, the term opioid was coined in the 1960s to refer to any chemical with morphine-like properties that isn't structurally an opiate. These compounds were originally developed to be less addictive and more powerful analgesics. Following the morphine rule, opioids have similar or stronger effects than opiates due to their masked structural homology. Each features a tertiary amine linked to an aryl ring. First is Demerol, also known as meperidine. It was synthesized in 1939 and advertised as a less addictive form of morphine, though it proved to be highly dependence-forming. Many industrial syntheses use the original method patented by the Isleb lab, where a di-beta-halogen alkylamine is treated with benzyl cyanide, leading to cyclization and nitrile hydrolysis to produce Demerol. An alternative synthesis by Haidt in 1959 features a quasi-Favorsky rearrangement. Treatment of monochloroketone 89 with sodium hydroxide induces the rearrangement. Two pathways are possible: migration of a phenyl group or a hydroxyl group. By comparing the A values, which measure steric strain, it's clear the phenyl group is much bulkier, making its migration less favorable. This explains why the desired product is the minor product of the reaction. Final Fischer esterification gives demerol. Next is fentanyl. In 1953, Paul Janssen set out to create a new analgesic that would improve upon morphine and demerol. He hypothesized that increasing lipophilicity would increase potency. This led to the synthesis of fentanyl through a 5-step process involving reductive amination, acylation, and amine deprotection and alkylation. Fentanyl is 50 to 100 times more potent than morphine. Given its powerful effects and ease of synthesis, it is often mixed with heroin and other drugs, frequently unbeknownst to the user. Methadone was synthesized in 1938 and exhibited stronger analgesic effects than demerol. It is now prescribed to treat opiate addiction. However, methadone itself is highly addictive, and many users end up cycling between opiates and opioids. The original synthesis starts with racemic 1-dimethylaminer-2-propanol, which reacts with sodium diphenyl acetonitrile to produce an aminonitrile. A final Grignard addition completes the synthesis of racemic methadone. Now we move to a different class of psychoactive drugs, the benzodiazepines. Research in the late 1950s to expand the ring of quinazoline 3 oxides led to their development. Leo Sternbach was investigating these heterocycles to replace the highly addictive barbiturates. A library of compounds he made went untested for 2 years until a colleague rediscovered them. They showed remarkable activity as sedatives, sparking a major development campaign. A series of benzodiazepines were synthesized and marketed as anti-anxiety medications. Others, like flunitrazepam, commonly known as a roofie, affect cognitive function, leading to abuse as a date rape drug. It was eventually demonstrated that benzodiazepines were just as addictive as the barbiturates they were meant to replace. Structurally, benzodiazepines are named for the fusion of a benzene ring and a diazepine ring. Most are 1,4 substituted. Let's look at diazepam, or Valium. After the discovery of the first benzodiazepine, Librium, Valium was synthesized and found to be more potent. It became the top-selling drug in the US from 1968 to 1982. The original synthesis began with an orthoaminobenzophenone, which was converted to a quinazoline 3 oxide in 3 steps. Treatment with sodium hydroxide caused this to undergo a ring expansion to a 7-membered lactam, which was then elaborated to Valium. Subsequent optimization reduced the synthesis to just 2 steps: condensation of orthoaminobenzophenone with glycine ethyl ester, followed by amide methylation. The first academic synthesis of Valium was achieved by the Gates Lab in 1980. They converted isotoic anhydride to a 1,4-benzodiazepine 2,5-dione. Acetylation and Grignard addition gave an aminobenzophenone derivative, which yielded Valium after deacetylation. Another common benzodiazepine is alprazolam, or Xanax, first synthesized by the Upjohn Company in 1971. Starting with a quinoline derivative, treatment with hydrazine, followed by reaction with triethyl orthoacetate, installed a 1,2,4-triazole ring. The next step is a fascinating transformation. Treatment with ozone, followed by an oxidative workup, gave ketone 1,14. The proposed mechanism involves the initial formation of a secondary ozonide. Iodide attacks the ozonide, causing it to collapse into an aldehyde and an equivalent of hydroiodite. This +1 iodine species is then reduced by more iodide to give molecular iodine, which in turn oxidizes the aldehyde. After deprotonation, a resonance-stabilized acylium cation is formed. Quenching with water gives a carboxylic acid, which, after protonation of the heterocycle, undergoes decarboxylation to yield the final ketone product. From there, hydroxymethylation, conversion to a chloride, and displacement with ammonia leads to cyclization and the formation of Xanax. Next, we'll discuss the stimulants. These compounds promote wakefulness and decrease fatigue, and range from caffeine to cocaine, amphetamine, and MDMA. Structurally, cocaine is a bicyclic troponone alkaloid. Amphetamine and its relatives are classified as phenethylamines. Let's start with cocaine. The euphoric effects from chewing the leaves of the Erythroxylum coca plant have been known for millennia. The coca alkaloid cocaine was isolated in the mid-19th century. It gained popularity as a local anesthetic, a cure for opiate use disorder, and an additive in products like soda. By the turn of the century, its addictive nature became clear, leading to the 1914 Harrison Act, which restricted its sale. From a synthetic perspective, cocaine's compact bicyclic structure has long attracted chemists. The first synthesis by the Willstatter lab in 1903 was a landmark moment, setting a new precedent for the complexity that chemical synthesis could achieve. The synthesis began with cycloheptanone. After several steps including bromination and intramolecular displacement, they formed the bicyclic core. Further functionalization, including oxidation, completed the synthesis of troponone, the core of cocaine. Treatment of troponone with sodium and ethanol and carbon dioxide, followed by esterification, gave a methyl ester. Reduction in benzylation afforded racemic cocaine. A final chiral resolution gave naturally occurring negative cocaine. In 1917, while trying to understand the biosynthesis of cocaine, Sir Robert Robinson demonstrated a much simpler synthesis of troponone. In a one-pot procedure, he mixed aqueous methylamine, succinaldehyde, and calcium acetone dicarboxylate. A condensation followed by consecutive manic reactions gave troponone. This elegant reaction laid the groundwork for understanding the biosynthesis of many alkaloids and eventually earned him a Nobel Prize. More recently, in 1998, Rappaport and co-workers reported an enantioselective synthesis of negative cocaine. Using the chiral pool as their source of asymmetry, they started with a derivative of D-glutamic acid. An Eschen-Moser sulfide contraction was followed by a one-pot sequence to give a vinyl amine. Catalytic hydrogenation and decarboxylation, followed by reprotection, gave an amino acid derivative. A KHMDS-mediated Dieckmann cyclization gave a bicyclic beta-keto ester. A series of steps including a Bamford-Stevens reduction and a 3+2 dipolar cycloaddition led to a 4,5-dihydroisoxazole. This was then elaborated over 6 more steps to give negative cocaine. Regarding its illicit use, cocaine is consumed in 2 main forms. Powder cocaine is the hydrochloride salt, used via injection or insufflation. Crack cocaine is the free amine or free base. It is far more addictive because it reaches the brain more quickly. The name crack comes from the sound it makes when burned. It is illicitly made from the salt by treating powder cocaine with aqueous sodium bicarbonate. Upon heating, the free base separates as an oil, which can be solidified. Now let's move to the phenethylamines, one of the most widely abused and produced classes of illicit drugs. Amphetamine is a stimulant that increases wakefulness and focus. Physicians prescribe it as a mixture of 4 different salts, sold under the brand name Adderall, to treat ADHD. This and other stimulants are often abused by college students as study drugs. The first synthesis of amphetamine was in 1887. A simple racemic synthesis from 1968 starts with phenylacetone and formamide. Condensation under Leuchart conditions, followed by hydrolysis, yields racemic amphetamine in just 2 steps. While effective as a racemate, the enantiomers of amphetamine have different effects. Plus amphetamine has higher potency in the central nervous system, while minus amphetamine has a larger effect on cardiovascular activity. This has motivated efforts to synthesize it in enantiopure form. One prominent method by Yamaguchi uses chiral aziridines. Starting with the chiral building block L-alanol, a chiral aziridine is formed. Treatment with phenylmagnesium bromide and catalytic copper chloride results in nucleophilic attack at the less substituted carbon. Finally, acid-mediated removal of the phosphonate protecting group reveals enantiopure plus amphetamine. Indiscriminate hydroxylation of the benzylic position of amphetamine leads to 2 sets of diastereomers. The erythrodiastereomers are the ephedrins, while the 3-O-diastereomers are the pseudoephedrins. Medicinally, ephedrine stimulates the central nervous system, while pseudoephedrine acts on the peripheral nervous system and is used as a nasal decongestant, sold under the brand name Sudafed. Mono-N-methylation of amphetamine yields methamphetamine, a commonly abused drug with street names like meth and crank. Due to its relative ease of synthesis, it's manufactured in many clandestine labs. These labs are often dangerous, with production frequently leading to explosions and fires. Synthetically, pseudoephedrine is a common starting material, as many routes exist for its reduction to methamphetamine. In recent years, a modification of the birch reduction known as shake and bake has become the method of choice for illicit methamphetamine synthesis. The process starts with crushing pseudoephedrine-containing decongested pills. These are added to a plastic bottle along with ammonium nitrate, lithium metal, solid sodium hydroxide, and xylenes, all chemicals available to the layperson from household goods. The bottle is then subjected to iterative cycles of shaking and venting. After the gas evolution stops, the reaction is filtered and acidified with gaseous HCl to give methamphetamine hydrochloride. Another major stimulant is MDMA, commonly known as ecstasy or Molly. It is a strong stimulant that prevents the synaptic reuptake of serotonin, dopamine, and norepinephrine. It also affects the brain's temperature-regulating mechanisms, and users can die from hyperthermia. Merck patented the first commercial MDMA synthesis in 1912. It began with safrole, a natural product. Markovnikov hydrobromination of the terminal olefin gives a secondary bromide. A Finkelstein reaction converts this to the iodide, which is then displaced with methylamine to give racemic MDMA. A more recent synthesis from the Schulz lab features a courteous rearrangement. It begins with the compound helinol, which undergoes a Perkin reaction. Olefin hydrogenation and conversion to an acyl chloride sets up the formation of an acyl azide. This undergoes a courteous rearrangement to an isocyanate, which is then trapped as a Bach carbamate. N-methylation followed by Bach deprotection provides MDMA. Clandestine MDMA synthesis often begins with the distillation of safrole from sassafras oil. A Wacker-Suji oxidation using palladium chloride, available as a photographic developing agent, yields the ketone MDP2P. Subsequent reductive amination with methylamine using a variety of reducing agents, such as aluminum amalgam, provides racemic MDMA. An interesting variation bypasses the need for the highly regulated methylamine by using the more readily available nitromethane, which generates methylamine in situ in the reducing environment. Our final class of drugs is the hallucinogens. Naturally occurring hallucinogens have been used for thousands of years. Many of these compounds structurally mimic neurotransmitters like dopamine and serotonin. In the mid-1960s, a counterculture movement in the United States campaigned for the decriminalization of one of the most famous hallucinogens, plus-I lysergic acid diethylamide, or LSD. Structurally, many hallucinogens share homology with either dopamine or serotonin. This is clear in the structures of mescaline and NN-dimethyltryptamine, or DMT. Careful inspection of LSD also reveals a resemblance to serotonin. On the other hand, ketamine and phencyclidine, or PCP, do not resemble these neurotransmitters, but still produce hallucinogenic effects. Let's look at LSD. In the midst of synthesizing amide analogs of lysergic acid, Albert Hofmann unwittingly created LSD. It wasn't until 5 years later that he would accidentally ingest a small amount and discover its psychedelic properties. While initially used by the medical community, LSD soon became a prominent recreational drug. Structurally, it shares a tetracyclic skeleton with clinically relevant ergot alkaloids like bergametrine and ergotamine. Industrial access to these alkaloids relies on isolation from fermentation or field cultivation. LSD can be made from the amination of lysergic acid or from the hydrolysis of related drugs. Therefore, the syntheses we'll discuss focus on creating lysergic acid. The first total synthesis was published by Woodward and co-workers in 1954. Starting from a known dihydroindole derivative, an acyl chlorination followed by a Friedel-Crafts acylation closed the C-ring. The resulting ketone was brominated and then displaced with a methylaminoketal. Acid hydrolysis revealed a diketone, which then underwent an aldol condensation to close the D-ring. 6 more steps completed the first total synthesis of racemic lysergic acid. In 2013, the Fukuyama lab published an asymmetric synthesis of plus lysergic acid. Starting with a chiral beta-hydroxyl hydrazide, they generated an acyl azide. An in situ Curtius rearrangement afforded an isocyanate, which underwent intramolecular trapping to form an oxazolidenone. After 3 steps, a ring-closing metathesis installed the A ring. Next, a hexcyclization closed the B ring. The authors demonstrated masterful control of the beta-hydrogen stereochemistry, which is crucial for the beta-hydride elimination step to proceed. 11 more steps transform this compound into plus lysergic acid. In 2011, Fuji and Ono published a formal synthesis of lysergic acid featuring an aminopalladation cascade that established the C and D rings in a single step. Starting from 4-bromoindole, they constructed an anion. A She epoxidation gave an epoxide, which was open to an enol. This was then converted to an alene, needed for the key cascade. The alene intermediate underwent a presumed concerted alder-ene reaction to form a tetracycle, which intersected with a previously disclosed synthesis, completing the formal synthesis. Ketamine is a molecule of many uses, serving as an anesthetic, analgesic, and a recreational drug known as Special K. The first synthesis was disclosed in a 1956 patent. It began with orthochlorobenzonitrile, which after a Grignard reaction, bromination, and imine formation, gave an alpha-hydroxyl imine. This was the precursor for the key step, a pinnacle-like rearrangement. Heating this intermediate in decalin resulted in a 1-2 migration to give racemic ketamine. More recently, a racemic ketamine synthesis was reported by Zhang and coworkers. It started from a ketone, which underwent a direct alpha nitration. Nitro reduction and subsequent reductive amination with formaldehyde yielded racemic ketamine. Research has shown that negative ketamine is more potent for anesthesia and analgesia than the plus enantiomer. This has motivated the development of asymmetric syntheses. Kyoka published the first such syntheses. The second one begins with an enantioselective Mukayama aldol condensation. The resulting beta-hydroxyl ester was reduced and acylated to form a carbamate. After dehydration, the carbamate was converted to an isocyanate. The mechanism for this step involves the dehydration of the carbamate to form an allyl cyanate intermediate, which then undergoes a stereoselected 3,3 sigmatropic rearrangement, transferring chirality. Finally, reduction of the isocyanate and reductive ozonolysis gave enantio-enriched HEH ketamine. Next is phencyclidine, or PCP. First synthesized in 1926, it was later investigated as an anesthetic called Cernal. It produced the desired anesthetic effects, but was also a strong hallucinogen, leading to its discontinuation in 1965. Traditional syntheses are based on common cyclohexanone precursors, making them ideal for clandestine production. One common procedure from Park Davis and Company begins with cyclohexanone. Reaction with sodium bisulfite, followed by aqueous piperidine and potassium cyanide, gives an intermediate known as PCC. Addition of phenyl magnesium bromide to the imine formed in situ provides PCP. Clandestine syntheses of PCP often follow similar routes and can be performed on a large scale. One such method is called the bucket method, based on instructions seized from a clandestine lab. The starting materials are divided into 2 buckets. Bucket A gets cyclohexanone and sodium metabisulfite. Bucket B gets piperidine and an alkali cyanide salt. The contents of bucket A are added to bucket B, yielding the PCC intermediate. In a third bucket, bromobenzene is added to magnesium turnings to generate a Grignard reagent. This is then added to the PCC solution to give PCP. Mescaline is the active component in the peyote cactus and has been used for thousands of years in spiritual ceremonies. It is believed to mimic the neurotransmitter dopamine. The first synthesis was by Spath and co-workers in 1919. Beginning with eudesmic acid, they formed an acyl chloride, which was reduced to an aldehyde under Rosenmund conditions. A Henry reaction with nitromethane then gave a nitrostyrene. Successive reductions provided mescaline. A later synthesis used lithium aluminum hydride to convert the nitrostyrene directly to the amine in higher yield. Our final molecule is N,N-dimethyltryptamine, or DMT, the active component in ayahuasca, a spiritual medicinal brew from the Amazon basin. Its biosynthesis in plants occurs via the shikimate pathway. The direct precursor of DMT is tryptamine, first synthesized by Shapiro and co-workers in 1956. Their synthesis began with a Michael addition between diethylmalonate and acrylonitrile. After reduction and cyclization, a Jap-Klingemann reaction gave a hydrazine, which cyclized in polyphosphoric acid. Amide hydrolysis and decarboxylation yielded tryptamine. Conversion of tryptamine to DMT then occurs under standard methylating conditions or through reductive amination. In conclusion, the authors highlight several key lessons. First, the field of psychoactive drug synthesis is rich with foundational strategies. But even with modern, efficient synthetic approaches, total synthesis is unlikely to ever match the efficiency of direct isolation or semi-synthesis for complex alkaloids like those from the opium or coca plants. Second, it is clear that the early exercises from a basic organic chemistry education are on full display in psychoactive drug production. Whether it's forming a six-membered ring with a Diels-Alder reaction or introducing a tertiary amine through reductive amination, these fundamental maneuvers are critical, whether in a state-of-the-art lab or a garage. A final point looks to the future. The United States is currently overwhelmed by opioid use disorder. While there are many social strategies to combat the problem, the authors suggest that perhaps a part of the solution lies in the hands of synthetic chemists, in our ability to develop new compounds that can address pain and suffering while minimizing the potential for addiction. And that brings us to the end of our exploration of this paper. We've seen how the intellectual pursuits of organic synthesis have provided the tools to create molecules that can both heal and harm, and how the strategies developed in academic labs have been adapted and simplified for industrial and ultimately illicit production.